Hey guys, welcome to another video for chemistry. In this video I'm going to be working out some of the problems from the review in your chemistry book. We're still working we're working on the energy sublevels and electron configuration. So that's mainly what this particular part has to do. This is section 3 in the chapter review. I'm going to work out some of the odd problems. We'll work out the evens in class, and then you can work out the rest through watching this video as a help, as a guide, and that'll go along with the notes that you take in lecture, and what have you, and hopefully also the demos and labs that we do will help. So we're going to go ahead and start this so that the video doesn't get too long. So I have here on the screen is page 167. I'm going to be working out the odds, so I'm looking at number 77 right here, okay? All right. So number 77, it says rubidium using figure 24, which is right here, this figure. Explain why one electron in a rubidium atom occupies a 5s orbital rather than the 4d or a 4f orbital. Okay, so you know, in lecture we talked about how electrons, when you're trying to put the electrons, when you're trying to house them in orbitals, there are specific levels that you need to fill up first before you go to the higher ones. Think of adding people into a hotel room. You typically want to first fill in, for our purposes, we want to fill in the first floor first, and then the second, and then the third, and then the fourth, and then you keep filling up the higher levels or the higher floors, the higher numbers, and you want to fill out the bottom ones first before you fill out the top ones. Okay, that's kind of the idea that we're working with here. So rubidium has a certain number of electrons. We can find that in the periodic table, but we're not really concerned about all the electrons. We're just concerned about the outermost electrons. And it's asking, why does it occupy a 5s rather than a 4d and a 4f? Now, if you look at these numerically, you'll see that it says there's 5s. It says, why is this 5s being filled up first before the 4d or for the 4f? Now, I mentioned before, like in a hotel room, you want to fill up the first floor, second, third, fourth, and fifth. Well, here it seems that we started filling up the fifth floor before we did the fourth floor sublevels, right? So this is kind of where it gets tricky, because the numbers that you see here, these coefficients or these principal energy level numbers, these they don't necessarily indicate which one is going to get filled up first. Okay? If you remember, by looking at the periodic table, when you were looking at the periodic table and we were talking about how you fill in the electrons, the D block goes up one and the F block goes up two. And because of that adjustment in the periodic table, and remember, I have a video on that also when you look at the lecture for electron configuration. So if you don't remember that part of it, go back and watch that video to get an understanding of what I just said. Okay, so because of that adjustment of the D block going up one and the F block going up two, that actually changes the way that we fill in the orbitals. Okay, because in actuality, the 5s orbital will come before the 4d or the 4f. Now I want to show you that in a couple of ways. Okay, first I'm going to show you the way that when I was in chemistry, when I was in general chemistry, this is the way that I did it that helped me out the most. Okay, and then I'm going to show you how you can do that same technique by looking at this figure here. But I'm going to show you the way that I did it. So anytime that I took a test or a quiz, one of the first things that I would write out, besides my equations, was this chart right here. So I know that there's 7 periods, right? So there's 7 s orbitals. And again, go back to my electron configuration and my orbital filling lecture online, right, in the same playlist. Okay, so there's 4s, 5s, 6s, and 7s. And one of the things that I want to keep in mind as I'm filling this out is I do want to keep it as symmetrical, or maybe not symmetrical, but as evenly spaced as possible. And you'll see why that's going to be important. And then I know that the p orbitals begin at 2 because there is no 1p. Okay, and these go all the way down to 7, so 4p. So again, I want to keep these spaced evenly. I want to be organized when I'm doing this. I don't want to just be haphazardly writing this stuff out because it can mess me up. 6p and then 7p. Okay, And then the next block that's going to come in is the D's, and the D's begin at the 3, because there is no 1D and there is no 2D. 3D, 4D, 5D, and it ends at 6D. And this all coincides with the periodic table. And then the F's, there's only two F rows, and they begin at 4F, and 5F, right? Okay, so this is what I would do next. So I go diagonally and make sure that your diagonals are all the same angle. So the first orbital that gets filled up is the 1s, 2s, 2p, 3p, 3d, and 4s. Okay, and then 3d, 4p, and 5s. And this is the orbital that is in question. So rubidium has enough electrons that I'm able to fill up all the way to the 5s. Okay. Now you'll notice that 5s came up first, right? So here it's saying, why is 5s show up first before 4d and 4f? As I continue, well, look what's next. After the 5s, it's my 5d, and then 5p, 6s, and then I get to my 4f. Okay? So what that means essentially is that my 5s is at a lower energy state, I'll do it in blue, than my 4d or my 4f. 4f is at a higher energy state than 5s, and 4f is at a higher energy state than 4d and 5s. That is why the electrons, as I put them in rooms, if you will, or orbitals, the 5s shows up first. Now let me show you how you can use figure 24 to do the exact same thing. So instead of making angles like I did, like 45-degree angles or 30-degree angles, whatever they may be, you can just kind of make straight lines. So which one's going to come up first? 5s, and then the next one is going to be 2s, and then 2p, and then the next one that shows up is a 3s. Now if you're paying attention over here, you'll notice that this coincides with this chart, 3s. So what's going to be next is 3p, and 4s. So which one shows up next? 3p and 4s. And then just above the 4s level, you get 3d. So 4s, and then here's 3d, and then 4p and 5s should become next. Okay, so here's 4p, and you notice that there's nothing on that straight line. And now as I make a straight line, you can say from the bottom of 5s, is there anything that shows up next? Well, the next thing that would pop up is 4d. So 5s, and then 4d, and then after 4d is 5p and 6s. Let's confirm that. So the next level is 5p, and then 6s. And as I go down 6s, what's next? 4f. And as it asked after 6s, in fact, 4f is next. 4f, and then 6d, 6p, 7s, 7s, 5f, and then 6d and 7p, 6d and 7p. So you can see that they correspond and they correlate. Okay? Now you can use any one of these that I just showed you. It's okay. My feelings aren't going to be hurt if you don't use what I did here. And you know, like I said, for me, it was just the easiest way. It just seemed to kind of make better sense writing it out this way than doing it this way. Because as you can see, when I was writing my straight lines, especially when you get up here, it can be kind of tricky. So you're like, okay, so you're like 5s, and then what's next? Okay, 4d. But then what's the next level? 6s or 5p? Well, you can notice that 5p is slightly lower than 6s, so you know 5p has to be next, right? And then after that, 6s, and then you got to keep going. Is it 5d or is it 5f? And you can kind of, to me, it's a little bit easier to get confused by doing that because they kind of are closer. And you know, you can make the argument that you know it can be confusing doing this also on the right side. But you know, to me, as long as you're making as long as your spacing is even, when you make the diagonal line, you should just hit whatever is next. You see? And for me, that just seemed to work out better. I was kind of somewhat of a drawer as it is anyway, so I trust my spacing and my lines a little better than you know than I did this. But that's okay. If you trust that, that's fine too. But for me, this was just easier to learn that way. Okay, so again, the idea of why this gets filled up before this one and this one is because 5s is a lower energy state than 4d. And again, don't get tripped up by the fact that 5 comes after 4. Um, Even though that is the case, don't the numbers themselves do not indicate the amount of energy that orbital has. Okay, so that's number 77. Let's go ahead and jump into another one. I'll leave this here just in case I need it. If I don't know, I'll erase it. So let's look at 77 right here. Okay. Oh no, 79. Light is said to have a dual wave particle nature. What does that statement mean? A dual wave and particle. So that's the key part right there. It's a wave and it has a wave and a particle nature. Well, simply put, Einstein kind of helped to figure this out. A wave function. So light has a wave function, right? Remember, it's like a photon. Light is like a wave of energy. If you remember the full spectrum, right? In fact, this is kind of showing the full spectrum from your reds all the way to your reds all the way to your violets. Well, it's a wave. It's an energy wave, right? But Einstein helped to kind of solidify the fact that energy, light, is when it's weird, and the quantum world is really weird because electrons are like a particle, right? It's a negatively charged particle, but it also has a wave function to it. So it's a wave that has a mass, right? A photon, but at the same time it's just a wave of energy. So it has the dual properties. Um, in fact, it occurs to me right now that there's a really cool video on that with Dr. Quantum where he talks about electrons and how they have that dual. It's like a marble, but it's also like a wave all at the same time, and it's really bizarre. And that's really the best way to explain that. Beyond that, again, the quantum world is a really funny, weird place, and paradoxical in the sense um, that you have something that is a wave, but at the same time it's a mass, and it can be either or and both all at the same time. And if that's confusing, then you're probably understanding it right. That's kind of weird to say, um, but yeah. So that's basically what that means. Is just that light has both a wave function to it, and it's also a particle. It has a mass, so it has both at the same time, and it can also be one or the other at the same time. Really bizarre stuff, but it's true. All right, so let me look at 81, and I think this will be the last one that I work out for this particular video because I'm not keeping track of how long this is getting, but I'm sure it's getting pretty long. So let's look at what it's asking here. It says how many electrons are shown in each element's electron dot structure. Okay, so we want to put these elements as an electron dot structure. And recall that an electron dot structure is one of the ways, it's one of the symbols that we use to illustrate how many valence electrons an element has. And valence electrons are simply put the outermost electrons. And the outermost electrons are the ones that are involved in bonding with other atoms. It's kind of like with you. When you're bonding with somebody else, it's typically your extremities that are involved, like shaking a hand when you meet somebody, or high-fiving somebody, or fist bumping. The outermost part of you is the part that is coming into contact with somebody else. Similar with an element, its outermost electrons are the one involved. They're the ones shaking the hands and grasping onto another element, and they're sharing electrons to make a bond. Okay? So the easiest way to do this is to actually go to look at your periodic table. And let's go to a periodic table real quick. The easiest way to find out how many valence electrons an element has is to look at its group. Remember, the periods are horizontal and the groups are the columns. So the first one is carbon. So here's carbon right here. Carbon is in this one, right? So we have group 1, group number 2, and then the D block, we skipped the D block. So group number 2, and then we have group number 3 and group number 4. So the group numbers are the easiest way to find out how many valence electrons an element has. So carbon has 4 valence electrons, And the way that we show electron dot structure is we draw the electrons signified by a dot around the periphery of the element, okay? And so you can do it clockwise. So you have 1 electron, 2, 3, and 4. And that's the electron dot structure for carbon. So it has 4 valence electrons. And so now remember, there are 2 electrons per orbital. So that means that carbon has one of the unique properties of being able to make 4 different bonds because I have 4 single electrons that are ready to shake hands with other elements and to make 4 bonds. And this is what makes carbon so special and why it's why all organic matter is made out of carbon, because it has, with 4 potential bonds, it has a lot of options, and it can make a lot of molecules and proteins because of the fact that it can make 4 bonds. All right, let's look at the next one. So the first one was carbon, and now let's look at calcium right here. So let's find calcium. Calcium is element number 20, and it's in group 1 and then group 2. So group 2, that means that it has 2 valence electrons. So calcium with 2 valence electrons, you can kind of just put those 2 at each end right there. And that is how you would draw the electron dot structure for calcium. Okay? And next is iodine. Iodine is right here. Okay, so this is group 8 and this is group 7. So that means iodine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. Okay, and so iodine has 1 lone pair of electrons. It has 1, 2, it has 3 pairs, and then 1 lone pair. And that 1 lone pair is very active, and it really wants to make another bond. Okay, so iodine, all the elements in group number 7 are very reactive because they have that 1 electron, that lone pair that really wants to make a bond with something else. So they're very reactive. So when I say very active, that means that they want to make a bond with something. They want to complete that octet, that 8, 2, whoops, the octet, that 2, 4, 6, and they want to make that 8. They want to have that 8th electron there. Okay? All right, let's move on to the last one, gallium. Okay, so gallium is right here. Okay, element number 31. So this is group 1, group 2, and group 3. So gallium will have 1, 2, 3. Okay, and that is how the electron dot structure looks for gallium. Okay, at this point I'm going to stop the video, and then I'll continue on with the next one, 83, 85, and 87. Okay, guys, good luck in your studying.